Namaskaram. In this session, we will introduce the concept inner product on a vector space. Okay, in 2-dimension and 3-dimension geometry, we can define the concept of angle and perpendicularity because we can visualize everything in 2D and 3D. But what about in higher dimension spaces? For example, Rn, in general Rn or some CAB like that. Okay, suppose in general vector space, the inner products defines this concept of angle and perpendicularity in general vector space. Okay, the definition of inner product. An inner product is denoted by these two brackets, and this dot stands for two elements. Okay, inner product between two elements. The inner product is denoted by like this. On a vector space V is a function from V cross V to R, satisfying following conditions. And what is V cross V? Okay, V cross V means set of all ordered pairs UV where U comma V belongs to capital V. Capital V is a vector space. U and V are the elements of capital V. Okay, they are called vectors in V. Okay, such set of all such ordered pairs is defined as V cross V. So inner product is a function on V, and this function from V cross V to R. That means image of the inner product is always a real number. Okay, and that function should satisfy some conditions. The first condition is inner product of UU is greater than or equal to 0 for all U belongs to V. Okay, so that means inner product between the same element. We choose a particular vector U from capital V, then you think about the inner product between UU, that should be greater than or equal to 0. That is the first property. The second property, the inner product between UU, both are same element, then that is equal to 0 if and only if U equal to 0. That means inner product between UU equal to 0, then the vector U should be 0. Okay, conversely, if the vector is 0, that is 0 vector from capital V, right? Every vector space has a 0 vector. So if U equal to 0, then their inner product equal to 0. What is the difference between these two zeros? We know that inner product is a function from V cross V to R. That means the value of the inner product or value of the function is always a real number. So this 0 stands for our real 0. This 0 belongs to real number. And what about this 0? This is U equal to 0. We know that U is an element of capital V. Capital V is a vector space. So this 0 is a 0 vector in capital V. You got it? That's the difference between these two zeros. And what about this 0? Yes, that also a real 0 because inner product is greater than or equal to 0. Okay, we know that inner product is a real number. Okay, next one is distributive property. The inner product of U plus V comma W is equal to inner product of UW plus VW for all U, V, W belongs to capital V. Okay, and one more thing, what about this plus? This addition is the addition between U and V. What about U and V? U and V are from capital V. It's a vector space. Okay, so this addition is the addition defined in the vector space V. Every vector space has a vector addition. Okay, so this is vector addition. And what about this sum? This sum is between two inner products, and we know that inner products are always a real number. So this sum is the addition between two real numbers. Okay, so this is our normal addition. Clear? Next property, inner product of lambda uv equal to lambda times inner product of uv for all lambda belongs to R. So lambda is a real number. For any real number lambda, our inner product function should satisfy this condition. Okay, last property, inner product of u and v is same as inner product of v and u for all uv belongs to v. Okay, so if a function from v cross v to R satisfying all this condition, then we can say that that function is an inner product on V. And one more thing, generally this space is a field in general. Okay, in general it may be a real number or complex numbers. Anyway, in this case we will consider only the real inner product space. That's why we take this side, our range as real numbers. Okay, so in general this may be a complex numbers. So we consider only real inner product spaces. Okay, so this is the idea of an inner product. So inner product defined on a vector space V. So first of all, V should be a vector space. We know a set is said to be vector space if it's satisfying 10 conditions with vector addition and scalar multiplication. Okay, and on the vector space, suppose we define a function from V cross V to R and satisfying all these 5 conditions, then we can say that that function is an inner product on the vector space V. Okay. Okay, consider an example. It is called a Euclidean inner product on Rn. We know that Rn is a vector space. Okay, so we are going to define an inner product on Rn. And what is x? X is equal to a vector x1, x2, xn transpose. So we treating every element in Rn as a column vector. That's why we put a transpose. Okay, and y is equal to y1, y2, yn transpose. Okay, so we can treat y as a column vector. That's all. Then inner product of xy is defined as sigma I is equal to 1 to n xi yi. That means x1 into y1 plus x2 into y2 etc. xn into yn. Okay, so this is the definition of inner product, and we can denote this inner product like this: x transpose y. Why? What is our x? X is a column vector like this. So what about x transpose y? X transpose means it become a row vector. Okay, like this one: x1, x2, etc. xn. Clear? Because x is a column vector like this, so x transpose is a row vector. That into y. What is y? Y is a column vector. y1, y2, etc. yn. So what about its expansion? x1, y1 plus x2, y2 plus xn, yn. Okay, same as sigma xi, yi, where I is equal to 1 to n. Clear? That's why we can denote this inner product by x transpose y. Okay, anyway, it is clear that this function, this is a function from Rn cross Rn to R. Clear? Because x and y are members of Rn and the image is a real number because all the xi's and yi's, all the xi's and yi's are real numbers. So this sum is also real number. Clear? So it is clear that this function, this is a function from Rn cross Rn to R. So it satisfies the first condition. Next, we have to verify all the remaining 5 conditions for this function. Then only we can say that this function is an inner product. Okay, so first we have to verify this condition. Okay, so first we are going to consider the case inner product between the same element. Okay, so we consider inner product between xx. Okay, we consider the same element, and by definition, what is this? This is equal to x1 into x1 because the actually in general x inner product xy is equal to x1 y1. Here both the vectors are same, so x1 into x1 plus x2 into x2 etc. That means x1 square plus x2 square plus etc. plus xn square. It is clear that all the x's are real numbers, so all the individual terms are greater than or equal to 0. Clear? So what about the whole sum? The whole sum is greater than or equal to 0. So inner product of xx is always greater than or equal to 0. This is true for all the x belongs to R. So it satisfies our first condition. Okay. So first one is okay. So next we have to verify this condition. Inner product of uu equal to 0 if and only if u equal to 0. That means we are going to consider inner product of xx equal to 0 if and only if x equal to 0. Okay. Okay. First we consider inner product of xx equal to 0. From previous case, we know that this is equal to x1 square plus x2 square plus etc. plus xn square. That is equal to 0. And if and only if what? All the individual terms are greater than or equal to 0. So sum of non-negative terms equal to 0 only when all the individual terms are 0. That means x1 square equal to 0, x2 square equal to 0, etc. xn square equal to 0. And this is if and only if what? Square of something equal to 0, that is possible only when the term equal to 0. So x1 equal to 0, x2 equal to 0, etc. xn equal to 0. Okay. So what is the meaning? This means what about our capital X? X equal to 0, 0, etc. 0. So this is the 0 vector. This is the 0 vector in Rn. Clear? So inner product of xx equal to 0 if and only if x equal to 0. Converse part is also very clear. If x equal to 0, 0, 0, then all the x's are 0, then their square times are 0, then their sum equal to 0. That means inner product of x equal to 0. So that's why I write this if and only if. Okay, so this is our second condition. So this function satisfies first two conditions. Okay, next we have to verify the third condition. That means inner product of u plus v comma w is equal to the distributive property. Okay. For verifying the third condition, we consider three vectors x, y, and w. Okay, w equal to w1, w2, etc. wn transpose belongs to Rn, and we consider this inner product x plus y comma w. Okay, and what is x plus y? X plus y means vector addition between two vectors. Okay, this is a vector addition. So we know how to define vector addition in Rn. Okay, how to define the component wise addition. So x plus y is equal to x1 plus y1, x2 plus y2, etc. xn plus yn. Clear? Transpose. You know, again it belongs to Rn because Rn is closed under vector addition. It's a vector space. Okay, then you can write the inner product between x plus y and w. By definition, this is equal to what? This is equal to x1 plus y1 times the first element w1, then x2 plus y2 times second element the w2, etc. plus xn plus yn into wn. This is the definition of inner product. Okay, next we can expand this. Okay, we can expand this one like x1 w1 plus x2 w2 plus extra xn wn. We consider these n, we group these n terms together. Then another n terms are y1 w1 plus y2 w2 etc. plus yn wn. We group these n terms in another set. Okay, then what about this one? By definition, this is nothing. This is the inner product between x and w. Clear? That is the definition of inner product. By the definition of inner product, it is clear that this is the inner product between this x and w. Right? And similarly, what about this one? This is the inner product between y and w. So this is true for every, this is true for all x, y, w belongs to Rn. Okay, so our function satisfies the third condition. Okay, next we have to verify our fourth condition. That means inner product of lambda u v is equal to lambda times uv for all lambda belongs to R. Okay, we consider inner product of lambda x y. And what about this lambda x? Lambda is a scalar, x is a vector. We know in a vector space there is a scalar multiplication. So we know that Rn has a special scalar multiplication. By definition of the scalar multiplication defined in Rn, what about lambda x? Yes, it's a component-based multiplication. So by definition, this is equal to lambda x1, lambda x2, etc. lambda xn transpose. So this is the definition of lambda x. Okay, so next we have to consider the inner product between lambda x and y. Inner product between lambda x and y, because lambda x also a member of Rn. It belongs to vector space. Okay, so by definition, what is this? Lambda x1 into y1 plus lambda x2 into y2 etc. plus lambda xn into yn. Okay, like this. And here lambda is common. It's a real number. We can take outside. So lambda into etc. plus x and yn. Then this is equal to lambda into, what about this one? x1 y1 plus x2 y2 etc. plus x and yn in terms of this function. Yes, this is our inner product of x and y. Okay, so lambda xy is equal to lambda times inner product of xy. This is true for every x comma y belongs to Rn and for all lambda belongs to R. Okay, so this function satisfies our fourth condition. Okay, this is okay. So first four conditions okay. Then we have one more condition. Inner product between u and v should equal to inner product between v and v. Okay, so next we consider inner product between x and y. Okay, we consider inner product of xy. By definition, this is the inner product. And we know that all the xi's and y's are real numbers. And this is the normal product between the numbers. That is commutative. That means we can write this as y1 x1 plus y2 x2 etc. plus yn xn. Because this is our normal multiplication between numbers. And what about this one? By definition of inner product, this is our inner product between y and x. and this is true for all x comma y belongs to Rn. Okay, so the function satisfies our fifth condition also. So now this function satisfies all the 5 conditions. So we can say that this function, this function is an inner product on Rn, and that inner product is called Euclidean inner product on Rn. Okay. Okay, clear. For example, we consider two vectors x is equal to 1, 2, 4 and y is equal to 5, 3, minus 1 in R3. We know that R3 is a vector space, and now we have an inner product on all the Rns. In particular, we have an inner product on R3. Okay, Euclidean inner product on R3. What is the definition of Euclidean inner product on R3? Inner product of xy is equal to x1 y1 plus x2 y2 plus x3 y3, because in R3 we have only 3 coordinates, 3 components. Okay, so what is the inner product between xy in this xy? Okay, by definition, this is our x1, x2, x3, or y1, y2, y3. Clear? So what about this inner product? This is 1 into 5 plus 2 into 3 plus 4 into minus 1. This is equal to, okay, this is 5 plus 6 minus 4. This is equal to 7. So Euclidean inner product between these two vectors is 7. Okay, now we are ready to define inner product space. An inner product space is a vector space V along with an inner product on V. That's all. Okay, first we consider a vector space. We know that a vector space means a set together with the 2 operations and satisfying 10 conditions. Okay, suppose we have a vector space and this vector space has an inner product. Suppose there is an inner product in this vector space. Then we can say that this inner product with this this vector space with this inner product is called inner product space. So an inner product space means it contains 2 things, one vector space and inner product on that vector space. Okay, so it is clear that Rn is an inner product space, because we know that Rn is a vector space. Now we have at least one inner product on Rn, or Euclidean inner product. Okay, so Rn is an inner product space. Okay. Okay, next we will see some properties of inner product, real inner product. First property is inner product between u comma v plus w is equal to uv plus vw. This is also another distributive property. Okay, and how to prove this? Okay, first we consider the LHS. So inner product of u comma v plus w. We know that here we assume that this is an inner product. Okay, then we have to prove this property. Okay, so since this is an inner product, then using the property 5, we know that inner product is commutative. So this is equal to inner product of v plus w comma u. Then you can apply our property 3, that is distributive. So this become vu plus wu, right? Again, we can change the order, we can reverse the order using property 5. So this is equal to uv plus uw. Then oh, it's okay, so that's enough. So now inner product of u comma v plus w is equal to inner product of uv plus inner product of uw. Okay, so that is his property. Second one, we have to show that inner product of u comma lambda v is equal to lambda times uv. Okay, we consider the left hand side, that is inner product of u comma lambda v. Using the property 5, we can reverse the order, is lambda v comma u. Then using our property 4, this become lambda into vu. Okay, and again you can use property 5, is equal to lambda into uv. You can change the order. Okay, so inner product of u lambda v is equal to lambda times uv. And next property, inner product of lambda u lambda v is equal to lambda square into inner product of uv. How to prove? Okay, we consider the left hand side, inner product of lambda u lambda v. Using our property 4, this becomes lambda times u comma lambda v, right? Then you can use this property. Using this property, you can take this lambda outside. So lambda into uv. This is equal to lambda square into here. So this is our third property. So these are the some properties of inner product. Okay, consider another problem. Check whether xy is this function is defined as 2x1 y1 minus x1 y2 minus x2 y1 plus 5x2 y2. Okay, is an inner product on R2 for x is equal to x1 x2 transpose and y is equal to y1 y2 transpose. Already we know that R square has an inner product that is called our Euclidean inner product. Okay, we know that Euclidean inner product is well defined for all the Rn's, including R2. Okay, in this problem, we have to check whether is this function defines an inner product. Okay, that means we have to verify that five conditions. Okay, let's consider the first one. Okay, what is this function between x and x, inner product? Actually, we have to check whether this is an inner product. Anyway, we consider xx. So what is xx? By definition, this is equal to 2x1 y1. Instead of y1, it is x1 itself, so 2x1 x1 minus x1 y2. So x1 is x1 itself, and what is y2? Y2 is again x2. So x1 y2, sorry, x1 x2 minus x2 is x2 itself. What about y1? Y1 means in this case x1, because the first coordinate of this vector, that is x1 plus 5 times x2 y2. So x2 means the second coordinate of this vector, and y2 means second coordinate of this vector. Both are same, that's why 5x2 x2. Okay, then we know that x1 x2 same as x2 x1 because this is a normal product. So you can combine these two, and this is x1 square and this is x2 square. So this becomes, okay, we have to check whether this thing is greater than or equal to 0 for all x or not. But this is not straightforward because, okay, we know that these two terms are positive, but we don't know what about the effect of minus 2x1 x2. Okay, so this is not straightforward. So we have to use a simple technique. So we are going to split this terms as like this. Okay, we take 1x1 square from this 2x1 square and we add a 2x1 x2. Then we consider we consider 1x2 square from this 5x2 square. Then what are the remaining terms? 1x1 square is there, that is x1 square. We add 2x1 x2, so we have to subtract it. So 2x1 x2 for cancel its effect. Then one more minus 2x1 x2 is there. Then already 1x2 square is here, so remaining is 4x2 square. Okay. Okay, next we group like this. Then what about this one? This is nothing, this is our x1 plus x2 whole square. Then we can combine these two terms, so that is minus 4x1 x2. Then this become, this is x1 minus 2x2 whole square, right? So our inner product of xx can be written as x1 plus x2 whole square plus x1 minus 2x2 whole square. It is clear that both the terms are non-negative because there is a square term. So what about the whole sum? Whole sum is greater than or equal to 0. So whatever be the x, inner product of xx, the function between xx is always greater than or equal to 0. That means this function satisfies our first criteria. Okay, next we have to verify the second condition, that is inner product of xx equal to 0 if and only if x equal to 0. So we consider one side, inner product of xx equal to 0. This means what? Inner product of xx equal to 0 means, in previous case, we know that inner product of xx can be written as x1 plus x2 whole square plus x1 minus 2x2 whole square. Okay, we can rearrange inner product of xx is like this. Okay, we have already seen in first case. So this is equal to 0. So this is our assumption. And if and only what? This is a non-negative term. This also a non-negative term. So sum of two non-negative term equal to 0 only when both are 0. That means x1 plus x2 square equal to 0 and x1 minus 2x2 square equal to 0. And again if and only if. a square equal to 0 only when a equal to 0. That means x1 plus x2 equal to 0 and x1 minus 2x2 equal to 0. Now we have two linear equations. You can solve it. How to solve? You take the sum of the, not sum, yes, better if you denote this by equation number 1, this is equation 2. We have to solve these two for x1 and x2. So you consider 1 minus 2. What is 1 minus 2? x1 minus x1 is 0. This is x2 minus 2x2, that is 3x2 equal to 0. So x2 equal to 0. Then you can substitute x2 equal to 0 in this equation. So this equation implies, equation number 1 implies x1 equal to 0. So x1 and x2 are 0. So what is our conclusion? If and only if x1 equal to 0 and x2 equal to 0. If and only if, what about our vector x? Our vector x equal to 0, 0. This is our 0 vector in R2. So inner product of xx equal to 0 if and only if x equal to 0. So it satisfies our second condition. Okay, next we have to verify third condition. That means inner product of x plus y comma w equal to inner product of xw plus inner product of yw. Okay, so we consider w equal to w1 w2 transpose. This also belongs to R2. And we know that what is x plus y, that is a vector addition between x and y. By definition, x plus y is equal to x1 plus y1 comma x2 plus y2 transpose. Okay, by definition of this function, what about this one? 2 times x1. What is x1? x1 is the first coordinate of x. So here instead of x, x plus y. So what is the first coordinate? x1 plus y1, right? x1 plus y1 into y1. What is y1? y1 is the first coordinate of y. So here our instead of y, w. So what is the first coordinate? w1. Clear? Then minus x1. What is x1? x1 plus y1. y2 is w2. Minus x2. What is x2? x2 is the second coordinate of x. Okay, instead of x, here x plus y. What is second coordinate of x plus y? That is x2 plus y2. So this becomes x2 plus y2 into y1. y1 is w1. The first coordinate of y, instead of y it is w. Clear? And plus 5 x2 y2. What is x2? x2 is x2 plus y2. x2 plus y2. Sorry, this is x2 y2. What is y2? y2 is the second coordinate of y. Here instead of y it is w. So it is w2. Okay, so this is x plus y comma w. Okay, next you can expand. This is like this. Expand and compare the terms like this. 2x1 w1 and minus x1 w2 minus x2 w1 and plus 5 x2 w2, and we have one more type like 2 y1 w1 minus y1 w2 etc. And using the definition of inner product, you can easily show that this is xw plus yw. Okay, that is your homework. So you can easily verify this portion. Okay, just expand and compare the terms like this one. Okay, then use the same definition. So anyway, this function satisfies the third condition. Okay, next we have to consider the fourth condition. So inner product of lambda xy. What is lambda x? By definition, it is lambda x1, lambda x2. So what is inner product of lambda xy? 2 into x1. The first coordinate is lambda x1 y1 minus lambda x1 y2 minus x2. What is x2? x2 is the second coordinate. So lambda x2. Lambda x2 y1 plus 5 into lambda x2 y2. Okay, this clear that lambda is common. You can take outside. So lambda into the terms, and this is lambda into what about the remaining term? That is nothing our inner product xy by definition. Okay, so it satisfies our fourth condition. Okay, next we have to verify our fifth condition. That means commutative. We have to show that inner product of xy is equal to inner product of yx. Actually, what is inner product of yx? This is inner product of xy, that is given. Then what is inner product of yx? So 2x1 y1, instead of 2x1 y1, this becomes 2y1 x1. Clear? And x1 y2. x1 is the first coordinate of first vector. So here the first vector is y. What is the first coordinate of first vector? That is y1. Okay, and y2. What is y2? y2 is the second coordinate of the second vector. If the second vector is x, its second coordinate is x2. Clear? And minus x2. x2 is the second coordinate of first vector. Here it is y2. y2 and y1. What is y1? It is the first coordinate of the second vector. If the second vector is x, its first coordinate is x1. Clear? Plus 5x2 y2. That is 5 x2. Instead of x2, it is y2. Instead of y2, it is x2. So this is actually yx. And what about these two? They are same or not? Actually, they are same. You can easily show that. Why? This one is, you can rearrange like this to y1 x1, and next we interchange these two terms. Okay, so this is actually minus x2 y1. You can write this as minus y1 x2 for getting this term. And instead of x1 y2, you can write this as y2 x1. Clear? And plus this is 5 y2 x2. This is same as this one. So this is equal to inner product of yx. Clear? So this function satisfies all the 5 conditions of our inner products. So this is a inner product on R2. Okay. So in general, inner product is not unique for a vector space. For a vector space, it may contain several inner products. Okay. At least in the case of R2, we have 2 inner products. One is Euclidean inner product, other one is this one. Okay. So depending on the situation, we will define suitable inner product on a specific vector space. Okay. Thank you.